It's about robotics for environmental assessment and sustainability. So I'm going to co-chair this session with Jason Gregory, who's a researcher at the Army Research Lab. So he's also going to be our first speaker to present his paper on human-robot teaming for safe, resilient operations in humanitarian applications.
Thank you. Good morning. This is a collaboration with Sarah Al-Hassani and S.K. Gupta at the University of Southern California. And so the context of this work is environmental assessment and humanitarian applications. That is because disasters are inevitable, whether they are natural or man-made. Disasters will always be a thing that we'll have to deal with. Naturally, as a result, humans will be in adverse situations because of these disasters, whether they're helping people in the scene, doing things like search and rescue, or they're helping the environment, such as firefighting. But all is not lost, and robots can help. In the context of this symposium, we're looking at robots that can do good. And at the highest level, robots can do good by helping humans, primarily in their working conditions. And so that is, they can either help the rescuer or the rescuee, provided that they're equipped with sufficient technology. So, if we have a disaster, the natural question is, what is the right team composition? And the first is, currently, a lot of teams are human-only. That is, humans go in, they're relatively efficient, but they have to accept all of the operational risk in the environment. Alternatively, we could go to the other extreme and do a robot-only team. And this removes the risk on the humans. However, these solutions tend to be very brittle, and failure could cost human life. So, it makes sense that there should be some sort of team composition in the middle, where there's both humans and robots. And we are asserting that it makes sense that humans can make high-level decisions and task robots to do the dirty, dangerous tasks in the environment. And so this alleviates the humans of operational risk, but still uses the robots efficiently and puts some of the risk, but not all of the risk, on the robots themselves. So here we have a field experiment where a single operator tasked 2 ground robots to go in and do some environmental assessment of getting to places, looking at things, and building up maps. So we have humans, we have robots, we have a disaster scene. Naturally, there are going to be ethical implications. And so the natural place to start is Isaac Asimov's law of robotics. Robots should do no harm to themselves, should do no harm to humans. But clearly he was not thinking of humanitarian application when he came up with these laws, because there are some ethical dilemmas that naturally arise. What does it mean to really injure a human? And if a robot were to injure a human but save a human's life, should it perform that action? According to his laws, the robot would not do that action because some harm would occur. A lot of very bright people have expanded on these laws, some of which have attended this symposium. We had an entire session yesterday, and the consensus was that there is no consensus on ethical robotics as it is right now. And we're not going to look to solve this problem in this work. However, we are going to look at some themes that we see kind of developing in the ethical discussion. And we notice 2 themes. First is the role of the human as it relates to its teammates. And the second is the role of the robots and their situated autonomy relative to their other teammates, whether it be human or robot. So we are asserting that there are 2 fundamental principles for ethical decision-making, specifically in the humanitarian context. First is humans must be in the decision-making loop. That is, there is going to be life or death situations that have to be handled. So naturally, humans should be making some of those decisions, and maybe even a majority or all. Second, uncertainty, risk, and failure are inevitable in humanitarian situations, and therefore they must be modeled and accounted for in techniques. So these 2 principles do not come without their challenges. First, humans are prone to making errors. They can introduce delays, they can give commands that are just flat out erroneous, and these are all in time-critical, safety-critical scenarios. So we want to alleviate this problem. And we are suggesting that we can generate alerts intelligently to kind of prevent these situations from either happening altogether or mitigating the risk and outcome if they were to occur. The second challenge, or our second principle, is that failure specifically failure, but especially uncertainty and risk, are inevitable. If you've ever done any field robotics, you know that nothing goes according to plan. There's a plethora of ways in which things can fail, and challenges will occur that must be mitigated. Some of which can be handled through better engineering practices, but not all of them. Sometimes there's nothing you can do about the terrain you're operating in, the communications degradation, the GPS degradation. So we are suggesting that there should be some low-level autonomy that the robots have to mitigate the uncertainty, risk, and failure, or at least handle them efficiently and intelligently to make low-level decisions to enable resilient operations, that is, mitigate the impact of failure. So, the remainder of this talk will be the discussion of these two proposed solutions and how they fit into ethical decision-making for humanitarian application. So as we said, we want humans to make very fast, intelligent decisions, provided that we give them the right information at the right time. And so you can think of this actually relating back to yesterday's talk as Gil and Wolfram had mentioned the Gordian for all for autonomous driving. This is somewhat analogous to that in the humanitarian application. We want to amplify the decision-making of humans, but not take away all of their decision-making capabilities. We want to have them be provided with some sort of blended envelope of control, as was used yesterday, so that they're not making bad decisions, but still have the full authority to make decisions. And so we're looking at human set triggered conditions, because each human is different. They might want to be notified of different things at different times. So things like wasted time, going through excessively risky regions, improbable rendezvous if you have to share information, redundancy in efforts, which lowers team performance, and just excessive travel time. And so you can think of situations where a human might issue commands to robots that either waste time or will never work. We want to avoid those situations. And so through our alert generation framework, we're asserting that we can enable humans to retask robots intelligently based on the alerts that we give them. And so our alert generation framework looks like this. Because I'm short on time, I'm not going to go through the details, the technical details of every single aspect, but it's made up of three major components. The first is a state machine simulation. And so here we want to take the team composition, the mission conditions at any given state, and simulate out what could happen for potential mission outcomes. This obviously has plasticity in it, and will dictate what alerts are actually generated. The second component is a MTL, or metric temporal logic formula generator. The idea here is that MTL is a mathematical framework developed in literature, and it provides a common mathematical framework for defining formula that specifies what could happen in a time domain. And it also allows you the capability to specify at a certain time to do a check for a specific time instance, as opposed to infinite time over a certain interval. And the third component is an inference machine. And so here is actually where the meat of the evaluation happens. So taking the simulations from a state machine and taking what actual conditions the human wants to be alerted upon, we can do some inference based on the deterministic data to say that something will either never happen or will happen with some certain probability, in which case an alert will be generated provided the conditions are met. So we have some preliminary results, and two of which we are very excited about. First, we've demonstrated the ability to issue alerts based on simulation. And so a very naive approach would be simply to do a standard Monte Carlo simulation over all possible situations, state definitions, and conditions. And this is computationally feasible because of the complexity of the environment, because of the complexity of the interactions between the agents. And so we've shown that through smart simulation, where we are artificially injecting and teasing out the very critical events, we can actually decrease the number of simulations to come up with a relatively similar probability of an event occurring. The second result that we're pretty excited about is demonstration of alert generation based on inference. And so here what we do is generate a state transition model based on what we currently know, the given information, the current team composition, and the tasks that have been assigned to any robot. And so here we can do a graph search algorithm and determine whether or not a state can ever be reached. And if it cannot, we can assert with certainty that there's a guarantee this event will never occur. And this is very important if you want to do a very highly critical, important task, for example, rendezvous. If a human were to issue a task like rendezvous to a robot, that will never occur. Humans should know this before the robot goes out to an impossible task. The second component to our ethical decision making is this low-level autonomy to enable resiliency. And so the idea is that because things will fail, the robot should be making decisions to adapt to the situations that they're observing and try and improve their own performance individually as well as for the team as a whole. And so the idea here is that we have an uncertainty-aware and failure-aware framework for decision-making for specifically whether or not a robot should attempt to rescue another agent, like another robot. Here specifically we're looking at robot-to-robot rescue. We're not delving into robot-to-human rescue. But the idea is that if you were not to rescue any agents, and agents will fail, your team size will be monotonically decreasing. And so if we intelligently choose when to go rescue a robot, we can manage the team size, but it may not make sense to rescue every single robot. Towards the end of the mission, you may be able to complete the mission without rescuing other robots. We don't really care if robots die. We only care if humans die. So the idea here is, again, we have three major components. The first is a policy evaluation. And so we assert for a given mission that we will do some specific action followed by some policy at specific times. And we can run this out in a very parallelized fashion and evaluate many different policy evaluations for a given mission. Second, we extract out the best policies from our evaluation, and this gives us, at a certain time, given a certain state vector, we know the mapping between that state and what we should do in the discrete time domain. However, this will never actually occur because it's very unlikely we will have this specific state at this specific time in the mission. So what we do for the third component is synthesize all of our policies through interpolation to cover the continuous time domain. Therefore, if we have a state, any given state in the mission, we have synthesized so that we can determine what the best action is. This is kind of an eye chart. I don't expect anyone to actually read these tables, but the idea is we have two major outcomes from this. First, we can reduce the probability of mission failure, which is great. We're showing some promise in this policy synthesis. And second, we can actually be robust to noise. And so we are choosing the specific state vectors in which we are simulating and evaluating over. Naturally, there's going to be some state estimation error. This is an active area of research, but our policy synthesis is showing that even with error in either a single component of the state vector or the entire state vector as a whole, we're still able to produce some very reasonable and promising results for failure probability reduction. So the major takeaways, team composition is a serious thing to consider for a specific humanitarian application. And naturally, because humans and robots are involved in the decision-making process, there are unique ethical decisions and dilemmas for humanitarian applications. This relates specifically to a lot of the discussion that we had yesterday for ethical, regulatory, legal, and morality discussions. And naturally, ethical decision-making is very complex in any domain, but very much so in the humanitarian domain. And finally, we have two fundamental technologies that we're excited about. Alert generation frameworks for high-level decision-making by the human, and robust or resilient autonomy for the low-level decision-making of humans, or for robots, excuse me. So with that, I'd like to open the floor for questions.
Hi. Can you give some examples of the trigger conditions and alerts?
Yeah. So some trigger conditions that we think will be valuable that we've considered are in the center of this slide. And so one evaluation that we did was very complex human command would be this robot should go to this region, explore this, then this region. If you see this, do this other thing. If not, go do this other thing. And so based on the conditions that are met and the conditions that a single robot might see, they might oscillate between two events and effectively get nothing done. Alternatively, a human might say for one robot to go explore this area and a second robot to go explore another area, forgetting that previously it had already determined that another robot should explore that. So that would be redundant exploration. things of this nature where you might forget, you might be overloaded, you might be fatigued, and so you're making not the optimal decision as a human for tasking your agents, but we can check for that. And so we can do either probabilistic or with certainty.
Thank you.
One more question?
Hi there. Great talk, by the way. What types of physical missions is ARL actually conducting, like those field experiments? What was like the overall scenario, or like the area you were exploring, and what types of like ground vehicles and sensor suites are you using?
Yeah, that's a great question. So for the example shown here, the mission specifically was the operator has a satellite image of a fairly large urban environment, probably 1 kilometer by 1 kilometer, and so that operator specified specific locations that they wanted information from. This is kind of indicative of what a search and rescue team might do, kind of using their expert knowledge. And so that's what these red cylinders are here. The robots are equipped with LiDAR to do the mapping. That's what you see these point clouds are. There's a camera in the front. GPS, but we do not rely upon GPS. We have GPS denied SLAM, an IMU to do the SLAM system. And basically what the robots would do is, based on what a human would task, to go to these different red locations, they would autonomously plan, autonomously navigate. Once they noticed that they were inside one of those red regions, they would take a snapshot and then hold on to that information, monitor their communications to the base station, and offload that data when they saw fit, and basically the communications maintenance of that. In terms of missions that ARL does, it's very much supported for Army missions in general. We don't come up with our own missions, we look to support what might happen in the Army. And it also is dictated by the specific research project that we're looking at. In terms of ground platforms, we have Packrats, Huskies, Jackals, Warthogs, aerial vehicles, off-the-shelf, Iris, no DJI, of course, Parrot drones. Does that answer your question?
Thank you, Jason.